time due to this web, actually a lot of activity. Earlier it was not so much.
Correct.
Okay, let us start. Thank you.
Please.
Good morning to all. I am Indira Rani from NCMRWF, and today we are gathered to celebrate the WMO Day 2021, and it is jointly organized by NCMRWF MOES and the India Meteorological Society Noida chapter. And World Meteorological Organization came into force on 23rd March 1950, as we know, and became a specialized agency of the United States in 1951. And 23rd March is celebrated as the WMO Day worldwide to commemorate the coming into force of the WMO and also to highlight the importance of the role that people and their behavior play in protecting the Earth atmosphere. So usually the themes chosen for WMO Day reflect the weather, climate or water related issues. And this year, the WMO Day theme is the ocean, our climate and weather. So, and it reflects WMO's focus connecting to the ocean, climate and weather within the Earth system. And there is another reason for selecting this theme that this also marks the starting of the United Nations Decade of Ocean Science for Sustainable Development, planned for 10 years from 2021 to 2030. And to start the event, first of all, I welcome our head NCMRW for Dr. Ashish Mitra to this meeting. Welcome, sir.
Thank you very much. First of all, I would like to express my sincere thanks to Professor Mohanty and Professor Eddy Rao, who agreed with a very short notice to be our guest of today's function. So Professor Mohanty and Professor Eddy Rao actually doesn't need any introduction, but people who are new and younger generation at NCMRWF. So very briefly, I'll tell Professor Mohanty, who was at IIT Delhi. Then he was for almost 5 years at NCMRWF. He was head of research and modeling. Then from IIT Delhi, he became professor and moved to IIT Kharagpur. Now he is at IIT Bhubaneswar. And he has contributed immensely in monsoon research, numerical modeling, tropical cyclone, and very recently in last 10 years, he has contributed immensely in extended range prediction in a agriculture ministry's project. And he has around 350 research papers. And out of that, if you see the research get 5,500 citations and his H index is 38. So we are very fortunate to have been associated with Professor Mohanty. And I remember when we joined in much younger days, he was our guide, and I was very fortunate to be in CSIT Delhi when I was a student doing my PhD. So thank you, sir, for agreeing, and our scientists will listen from you. And regarding Professor Eddy Rao also, many of you know, but some of you who don't know, he was my senior in IIT Delhi when I was doing PhD with Professor Dubey. And many of you who are now who are exposed to ocean modeling, you will be surprised that ocean simulation, ocean modeling started in CSIT Delhi. I think that's the first in the country in 1980s, I will tell, in late 70s. And Professor Rao has worked immensely on the storm surge simulation, 3D ocean modeling, upwelling, and what we call 3D ocean circulation model nowadays actually was the 3D upwelling model, because my association at IIT Delhi, I was watching all these things. And after that, he has worked on internal waves and coastal process waves, and very recently also in the tsunamis. And he has also published a lot of paper, around 200 research papers in very good journals. And his citation index is also 2000, more than 2200. So thank you, Professor Rao, for agreeing to be part of our this WMO celebration. And what Indira said, I would like to once more repeat. I wish happy World Meteorological Day. Congratulate all associated with meteorology. And we are celebrating this because we should be proud that we have adopted this profession, being a meteorologist, weather scientist. And we should celebrate because we are contributing to the community to protect lives and property. So it's a big work we are doing. So like any other big day, we should be in the celebration day today, because we are contributing and we will be contributing. We are committed to this subject. So with that, I will welcome once again Professor Mohanty and Professor Eddy Rao. Thank you. Indira, you are muted, or I am not able to hear.
Actually, now I request Professor Mohandi to deliver his address.
At the outset, very good morning to all of you, and my hearty greetings and congratulations to all the community of NCOWF on this WMO Day. You can hear me, na?
Yes, sir.
Yes, sir. Yes, sir.
Okay. So if there's any problem, because this is a good thing that we could meet actually in the same day, we can meet several places. That is what Dr. Mitra told. It is possible because of the COVID, we have switched over to webinar and so on. So today, actually, I have already committed for another talk in the afternoon. And so now I'll give my talk very brief, rather my experience, why I entered to this area. Let me connect to my new graph. Can you see my PowerPoint? Dr. Mitra? Dr. Mitra, can you see my PowerPoint?
Yes, we can see. We can see.
Okay. So actually, I will give a very brief thing, but actually, this is a very befitting that you have the ocean, our weather and climate, because as we know, all the ocean and atmosphere, they are intimately linked. Though we are telling that Center for Atmospheric Science, we produce very eminent scientists like Dr. Mitra. He is a early oceanographer. He started with atmospheric science and became oceanography, and then now he's a coupled ocean modeler. So ocean and atmosphere are intimately linked each other, and the ocean that we are dealing, actually, as you know today, this is actually so much related to weather and climate over particular over India. Whatever you tell, whether it's a monsoon, whether it's a tropical cyclone or severe thunderstorms. So all these processes, they are intimately linked with the ocean. When we have learned a little about the ocean, then we are telling that the ocean is very passive. Its interaction with the atmosphere is a very long time, and we can take ocean as a steady state, or we take a ocean as a fixed SST and integrate our short range, medium range, or even external range. That is what we are thinking earlier. And this is because of really our less in understanding about our own ocean. But when India is concerned, you see that you know that the Indian Ocean, it is so vital for the Indian weather and climate. We cannot ignore at any stage its dynamic interaction with the atmosphere. So I will start with a very thing which you all know perhaps about the evolution of our atmosphere and ocean. So already it comes question that whether first starts atmosphere or first starts ocean, and how we are unique, our planet Earth, compared to that of the rest of the planets, that we have the water. And we tell that water is the life. But then if we see the evolution of our atmosphere and ocean, then we can go back to as early as 4.5 billion years back before the Christ, where actually, when actually after the origin of our Earth, then we have started first a atmosphere, which was outgassing from the interior of our Earth system with hydrogen and helium. It is both hydrogen and helium, as you know, they are very light gases, so they are easily escaped from our planet. And so then actually started, we have the volcanic eruptions. Then we have also comets from other planets. They come and burn in our atmosphere. So with that, we got a lot of carbon dioxide, water vapor, and nitrogen. Then as our atmosphere became cooled down and so on, as you know, then this water vapor started condensing and we get the precipitation rainfall. And these rainfall started runoff and going to the low-lying area. And that's how the ocean is formed. And now you know that more than 71% of our Earth's surface is covered the ocean. And ocean carries almost 97% of our water mass of our planet, where atmosphere contain only 0.02 percentage of the water as a water vapor or liquid water or ice crystals. So it's a very teeny part, but then most of our life, we depend upon this water, which is actually evaporate from the ocean and became available as a fresh water through the process of the condensation and precipitation. Therefore, first life generate, actually that time we have not much oxygen was available, though we have a water vapor is there, nitrogen was there, and a lot of carbon dioxide was there. But with the rain, this carbon dioxide started dissolving. And then actually first life was the cyanobacteria. These cyanobacteria developed in the water, and the cyanobacteria carry the photosynthesis. In the process of photosynthesis, CO2, water vapor, and light that lead to us release of oxygen, as you know, by the photosynthesis. So by this way, oxygen started releasing, and when more and more oxygen started releasing, then we got the life from the our planet. So therefore, this process started with the atmosphere and ocean, and both are intimately linked to each other. Because if you now visualize a atmosphere, it has no boundary. Neither, as you know, that neither we have lateral boundary, nor also we have boundary alone standing in the atmosphere. Atmosphere is linked with hydrosphere, that is our oceans, lakes, and river systems, and so on. It links with the lithosphere, it links with the biosphere, cryosphere, and outer space. So all these spheres, they are intimately linked. And as we have developed our more and more understanding of the subject of atmosphere, because you said, as Dr. Mitra told exactly, meteorology or weather science is such a science which is intimately related with each and every individual. He may be a beggar in the street, or he may be president in a palace or king in a palace, but everybody needs the weather. Of course, we learn many branches of science, the basic science we call physics, chemistry, biology, mathematics, and so on, but an applied science, but atmospheric science or weather science, it both have a basic science as well as an applied science, but this is a science for the common man. That is what I feel. And then if you see the contribution of, because if you see the contribution of science to society, particularly atmosphere science, it is immense. I came from a place that is close to Paradip, and when I was a small child, we are always fearing for the tropical cyclone. Once the monsoon comes, then we are fearing for a lot of rain and flood. We are going to high land, somewhere elevated place, because that time not a Pakka house, all are the Kacha houses, and we are fearing that if a cyclone will come, whether we will survive or not. That led to me, even after I completed my physics in solid physics specialization, I felt that this is a science which I should pursue, because this has linked to me day and night out, because sometimes I was going to school at the time I come so much rain that I have to swim to come back to my home. So that actually helped me to be fascinated to the meteorology. And when I thought meteorology is a science of atmosphere science, but that I was knowing only by the word. But my aspiration that whether we can predict the tropical cyclones and floods in my own region, that was my narrow thinking was at that time. And as you know that the service of the atmosphere science to the humanity is so much, it is almost encompass all aspects of the life. And for example, actually, I will give that talk in the afternoon. The tropical cyclone, 99, Odisha super cyclone, government record is more than 10,000 people died. But after that, the next one came to this same region, 2013, Thailand, where actually death was confined to 20. The remarkable change from 10,000 to 20, that means by proper prediction, because in 99, when actually we predicted the cyclone, I remember at the end moment, IMD told that you can let a peace model show that a cyclone will be going to cross West Bengal and would decide the shape. Unfortunately, it has not happened. It crossed the Odisha coast, more than 10,000 people died. Because the tropical cyclone is more example of the ocean and interaction with the atmosphere. That's why I'm telling you this story. And now in 2013, 5 days in advance, the prediction was so accurate that it will be around 50 kilometers either side of Gopalpur. It is going to cross. And after 5 days, the same thing happened. Odisha could evacuate 10 lakh people from the coastal area. And showing the example of 99 that if this happened and do not go, you may face the same fate. So people are evacuated and death toll was confined to 20. And out of that, 10 or 12 due to flood in the North Odisha, far away from cyclone area, and hardly less than 1 digit people there perish due to the tropical cyclone. That is the remarkable thing the meteorological community have done for mankind. So that's why the role of the meteorology to mankind. And I remember when we were secretary at that time when our NCMW was established, the secretary was Professor Ramarao, and then after that we have secretary was Dr. So that time they told that if I have my second work, then he was a physicist. I really like to be an atmospheric scientist. So this shows that the fascination of the atmosphere science and the complexity of the atmosphere science. Till we have done so much, till we have a lot of uncertainty. We tell that our science is still remain with a forecast. Forecast means a forecast, it cannot be exact. And that all you know that because it is not a, it is a having a degree of freedom is such large, and it has so much interaction with the hydrosphere, lithosphere, biosphere, cryosphere, and atmosphere that actually when you formulate a model, suppose you have to understand each and every aspect of the interlinkage, interaction of these processes so that you can develop a coupled system to have a better understanding. When we don't have an understanding, then we feel that, okay, it's very simple and all things, what is there, it's a mathematical problem to solve. That is what sometimes people, when they enter the subject, they feel what is there. At science is just mathematics of few equations which you are used in our basic degrees. But as we go more and more the science of atmosphere science of weather and climate, we see that with more and more linkage, and most important linkage is with the ocean and land. Therefore, this is a science which needs observations, because this science cannot exist without observations. This is geoscience, or that's why we have the Earth system science we call, because it is encompass entire parts of Earth and atmosphere, hydrosphere, and so on. So it needs observations, and the observations gives us a understanding, and that understanding leads us to develop the models, and the modeling ultimately help us to prediction. So our objective at the end that to give a better forecast to all community and all stakeholders and different stakeholders have different type of requirements, but that can be accomplished only by the taking more and more observations and to have a greater understanding. Till, as we know that we know a little drop of the ocean, like we tell, similarly, we know a little bit of the entire gamets of the weather and climate systems. So therefore, I feel this is a science which cover almost entire all the branches of the basic sciences, like weather and climate sciences. If you see, it involves the physical science, because the atmosphere is in motion, there's the thermodynamics of the atmosphere, there's the physical processes like radiation, turbulence, convection, and so on. All these gamets, they belong to physical science. Similarly, we need the mathematical science, because you know that all of you know that you are all modelers, so I should not tell you that this modeling, which needs mathematics, and use that we want numerical analysis, we need the data assimilation, though we get observations, to take the observations and get things out of that, it needs a very complex assimilation system. People, those who are not in meteorology, they feel assimilation is nothing but it's interpolation. But in the science or sense, it is maybe a simple interpolation, but those who are working the data assimilation, you know how complex it is. It is more complex than the model itself. How to take variety of data, how to make the quality control, how to make them consistent, then how to make it that the whole globe, we have only observation available, only one-third area, remaining two-third areas we don't have observations. How to make it more realistic? And most of our problems that we make a lot of assumptions, because that is our limitation of observations and assimilations. So all these things on the mathematical sciences like numerical analysis, partial differential equations, and fluid dynamics, we have to make a lot of assumptions, because in the real atmosphere, processes are continuous, both in the space and time. But we cannot take observations continuously in both space and time. So we have to discuss it. And though it is again a simple thing of partial differentiation and so on, but in reality, when you implement, you know that the problems associated with that, how to make it more faster and so on, and how to make it more effective and so on, and how to avoid the truncation errors and so on. It is really a challenging problem. Similarly, chemical science, which that now as we more and more understand the atmosphere, we have so many pollutants and gases and aerosols, we have the water vapors, we have solar light. So a lot of chemical interactions take place. As we understand more and more the chemistry, then we know that it is became actually, we have more chemical interaction than our biological interaction, as we have the 7 equations, as we all understand, for 7 basic parameters, but chemical reactions we may have 2000. Similarly, the biosphere. Biosphere, you know that we feel that the biosphere exists with the atmosphere, because atmosphere gives the rain and so on. But biosphere also equally important, because our evapotranspiration, the land use, albedo, surface roughness, and so on, in that thing played important role, and how to bring the water from the subsurface to the atmosphere and make evapotranspiration and so on. And you know, deforestation and all these things, how it is an important role. Similarly, the earth science, lithosphere, cryosphere, soil characteristics, surface hydrology, and so on, environmental sciences, computer science, you all know. So all these branches of science, they are intimately linked with the weather and climate science. So therefore, we tell that weather and climate science, whether it is a basic science or is a engineering science or a application science, whatever you tell, it fits with that, the way you interpret this subject. So therefore, atmosphere science is a science really for the actually all branches encompass all the branches of science. Similarly, if we see the development of the models with which you are now all are comfortable, if we see now the first computer came only in 1950s, 1948 exactly, and 1950s.
अरे यार तो वो बाउंस कर रहा है
Yeah.
तेरा ये
देवाशीष म्यूट करो, देवाशीष म्यूट.
So therefore, actually, up to 1960s, we are knowing only atmosphere and we are satisfied with the atmosphere. And we are thinking we know everything if we know the atmosphere, and we have the atmosphere model. But in 80s, we came to know that atmosphere is not standalone. It depends upon the land. This is land surface processes, lithospheres, and biosphere, cryosphere. They all are part of the gamets of atmosphere. And ocean came into the modeling in the 1990s because we don't have ocean observations. We don't have so much ocean observations. It is the Argo systems which came only of this century, that in 1999 is the first is conceived, and 2000, 2005 or so on, that is the period Argo system was deployed. And now, like our radiation observation RSRW, this Argo system, actually that make a big revolution to have a ocean science, to be intimately linked with the atmosphere science in all scales, even short range prediction like tropical cyclones, or to the medium range prediction or monsoon prediction, so on. Everywhere ocean plays as important role as that of the other processes. And in 1990s, we also came to ice, and particularly the sea ice. Then 2000 came the sulfur, sulfate, and so on. And then comes the carbons, and then comes the atmospheric chemistry, and so on. So as we understand more and more, we know that we know more high resolution models because the whole process is continuous. And we know that if we improve the computing resources and we have finer resolution, and if we have the including all these complex processes, we can have a better modeling system. Because same way also, we have the zoo of the models, as we see that the various type of models that we deal with. And now actually ocean is actually in all aspects, as I told, the couple models now used, not only actually when we, ancient WF, we started with Dr. Mitra, Dr. Kar, Dr. Prasad, and everybody. At that time we are telling, okay, ocean SST is there, we are very fine and go on. Because we are not understanding so much about the ocean that time. We don't have ocean net at that time. So you have to stabilize the ocean by running for hundreds of years, and that's why we are thinking that it is only the climate. It is not, though we know that the tropical cyclone, thunderstorm, or monsoon, they are genesis over the ocean, or the ocean is the cause of the maximum water vapor, and that is the thing. But still, then we don't have the observations. That's why we are telling that, okay, ocean for the short range prediction of tropical cyclones, its life cycle, its intensity, it cannot be predicted without a ocean coupled with the atmosphere. Therefore, this type of understanding, we started with the large scale area models. Again, that is due to limitation of the computing resources, the cloud reasoning models, weather prediction, predict models, global climate models, and so on. So we have got a different set of models, but at the same time, we have to look for the ocean as one of the very important parts. So it is very befitting that ocean science has taken so much lead role that the WMO has taken it in one of the theme, and the United Nations has taken it a theme for the 10 years or decades for the science of ocean. And there actually more emphasis that how to save our ocean, because ocean is containing 71% of the area coverage of the whole globe, but it is going on polluted, it is going on destroyed its health characteristics due to various human activities, like our use of a lot of plastics, plastic products, and so on. All is actually never degraded. It is going on with water and so on, and finally deposited in the ocean. Ocean try to, like atmosphere, ocean try to observe everything, but it is gradually deteriorating. So to sustain full development of the ocean is now a bigger issue for all of us for the sustainable development of the mankind. In that respect, ocean plays a very important role. And I think with this, perhaps my time is over. I think, Dr. Mitra, my time is over.
Another 2 minutes.
Okay, so then I will leave it here because I kept something on time change and tropical cyclone, but I think it will not have a time. And as Dr. Mitra told, that we have also some other program after the launch also. So with this, again, I thank you very much, Dr. Mitra and the scientists of the NCOWF to inviting me to this very auspicious occasion for the meteorologist of the, as it is, we call that is the birth of the atmosphere science day, because meteorology now, without a WMO, has not much distance, because though we have friends and enemies and so on as political things, but when we come to science of the weather, we have to know entire globe. We have to, whatever observation we get, global observations, we get everything as you know in a fraction of a hour or so. That means the observation may be in any part of the world, but it is available in few minutes at, on your table with your computer. And without that observations, we cannot go ahead. And we always struggle that we should have more and more observations required. And in that respect, actually, observation for the ocean is a very important role, and integrating the assimilation of both ocean and atmospheric assimilation. When time will come, they can be integrated together, because now we have atmospheric data assimilation, ocean data assimilation, but a time will come, perhaps we have to combine all these things. And so also the science of land, atmosphere, ocean, and all things, as I told you, that have to be combined intimately so that we can predict the weather and climate seamlessly, starting from very short range, now casting that of the climate and climate change in a single suit, which needs enormous computers, enormous observations, enormous scientific manpower, and our understanding of processes. With this very auspicious day, again, I have all my best wishes to all your team of NCOWF scientists to flourish, because this is a center built that time, center for modeling in the country. And it is maintaining, and it will maintain not in the country, in the whole world. And all of you know also that our ancient of the model is now one of the art power model with any of the developed countries in the world. So this is our pride. So I think all of you will maintain it. And in that, obviously, ocean and atmosphere, weather and ocean, they are intimately linked. With this, I have my all the best wishes to all of you. Thank you very much.
Thank you, sir. Thank you very much for the very informative talk. And you already conveyed that Earth system science is the queen of all sciences. Thank you very much, sir. Next, we have our guest speaker of WMO Day, Professor A.D. Rao from IIT Delhi. So I invite Professor A.D. Rao to deliver his address. Professor A.D. Rao.
Yeah, thank you. Thank you. I think Professor Mahanti has to dish share actually.
Yeah, dish share, how to dish share. Sharing is very
sharing
good.
And
stop sharing.
Stop the sharing. Yeah.
Stop sharing.
Right. Okay, that's fine. Okay. So now I will use my. Can you see my screen?
Yes, sir.
Okay, thank you. Let me put it in the slide mode. Okay. Thank you, Dr. Mitra, for inviting me for this talk on the auspicious WMO Day. And on this occasion, I would like to wish you all for the best of science would come from NCMRWF scientists. Okay, so today actually I have chosen my topic, recent developments in the computation of I think in the side it is coming all the photos. Okay, let me how to.
Yeah, you can minimize that. Photo works.
Yeah, I think I have to minimize. Okay, right. I could do that. Yeah, this is the topic which I have chosen: recent developments in the computation of coastal inundation in response to a tropical cyclone. Why I have chosen is that we all know that for any cyclone, inundation is associated because a lot of water levels at the coast that will lead to coastal inundation. So far, what we have been doing is that for a calculation of coastal inundation, we are not taking into account of the precipitation. That's a huge, actually. The cyclone produces a lot of precipitation during the event, during any tropical cyclone event. Therefore, we have to take into account of the precipitation. It's a very important component, but nevertheless, also we need actually how much freshwater discharge is coming from the river systems from the upstream end. So these two components we did not take earlier. So for the last 1.5 years, we have been actually working on this one to get into how to incorporate these two factors. One is actually precipitation associated with any cyclone, and another one is that freshwater discharge. These are the things for which actually we have used a coupled hydraulic HECROS. This is called HECROS, developed by US Army Corporations of Engineering, USASC, very famous actually. And EDSERC model that is also developed by US. But these two models actually, of course, EDSERC we have been using for quite a long time. In fact, our center is the first to start this usage of EDSERC. Then we coupled these two, coupled hydraulic and HECROS to incorporate the precipitation and upstream end of the river discharge. These two factors. Okay, so this is a very huge work, but today I will just give a glimpse of how it is done, how much it is important, how much it is contributing on the part of inundation. All these things which I would like to discuss without going into the much technical, because it took about 1.5 years, the whole work actually. So I would like to just give a brief idea about how we have proceeded this work. Okay, so for this actually, we have used two cyclones. One is actually a 1999 cyclone. This cyclone exactly was crossing in the Mahanadi Basin. That's very important. It's just passed through the Mahanadi Deltaic region. And another cyclone, which was a recent one relatively, that is a Phylin cyclone, is just 100 kilometers south of this Mahanadi Basin. So we have selected these two just to see how much impact on the inundation by considering the precipitation into account and also freshwater discharge. That's the idea of taking these two cyclones. Okay, and these are all, you know that actually how much these are the characteristics of the intensity of the cyclone, but I don't have to tell you, you all know it. 1999 is a super cyclone, and Phylin is also a very severe cyclone, but it's not to that extent of 1999. But how much precipitation it was occurring, like you could see that this is the area average precipitation per day. Okay, you can see on each day, because that is also our forcing into the model. So this is for the 1999 cyclone, and this is 2013 Phylin cyclone. You can see how much precipitation. Okay, and the most complex procedure for incorporating the river channels. This is very complicated. It took long time for us to incorporate the cross sections of Mahanadi basins. Okay, there are so many tributaries. You all know that Mahanadi has got so many, and Brahmani and Baitarani. All these things we need to incorporate proper configuration of these tributaries. That's very important. So I don't want to go into the details of this one, how we have much effort we have put it. We have used the Google Earth data also for this one, and also SRTM data. And SRTM data is modified by using the Google Earth. And also we have got some cross-sectional data at some points. So we have used that one also into this one, and then modified the entire configuration of the river system to mimic the realistic one. So how much realistic is, I would not say that it is very realistic, but it's whatever the possible way which we can use in the limits of available data. That's what we did actually. Okay. So SRTM data, you all know that one, it's available. So we have modified the SRTM. Right hand side is the SRTM data, okay, for the Mahanadi Basin. You can see that all the tributaries are not well configured in this one. Okay, all the tributaries are not properly incorporated in the SRTM data, but we modified the SRTM data in order to get the actual river basin. So you can see on the left hand side, the rivers are well actually represented compared to the SRTM yellow data. Okay, so you can see the channels here, and from the upstream end of these rivers, we have used the freshwater discharge on daily basis. So we have used that one, and from the south side, okay, we have in the, I think in the next diagram you can see 1, 2, 3, 4, 5. These are the actually mouth of the different tributaries of the Mahanadi Basin. Okay, all these tributaries are joining the Bay of Bengal at 1, 2, 3, 4, and 5. So we have represented this mouth of these tributaries more accurately. Okay, so from this side, we are giving the storm tides as the forcing. From the upstream end, you have freshwater discharge. Over the region, you have precipitation. So you can see the coastal inundation or inland inundation due to 1999 cyclone and Felin cyclone, how it makes the difference. That's what we have seen in this work. Okay, so this is the discharge from the upstream end for Brahmani and Baitharani and Mahanadi. This is for 1999 cyclone. We calculated from the CWC all these things, we got it. And here, if you use the first one is we are doing for the 1999 cyclone. The first one, is spatial coverage of coastal inundation and maximum water levels with the daily river discharge for 1999 super cyclone. Okay, and this is actually this is the aggregate response of without and with discharge. This is without discharge. This is with discharge. You could see that how much discharge is impacting on the computation of coastal inundation. That's very important. Okay, so you will get additional areas because of the freshwater discharge. Okay, so because there are two kinds of flows which are coming in the opposite direction, and that leads to over banking flooding. Actually, that's why you get more area is getting flooded. So all these things actually, we have made actually one video out of that one, but I am unable to show here because of shortage of time. But how the water goes from the seaside, how the water comes from the upstream end, and how it leads to wave-wave interaction, and which leads to a kind of over flooding from the banks. That's very important. Okay, so this is actually, and out of all these tributaries, Brahmani is contributing more actually for the calculation of inundation. It is actually because more freshwater discharge is coming from the upstream. For 1919 cyclone only I'm talking about. Okay, this actually Brahmani river is contributing 50% of the inundation. That's very important. Okay, so this is that LULC, land use land cover data. We have used actually because your bottom roughness and surface roughness changes by using the LULC data. So this gives a better representation of coastal inundation because you are properly defining, depends upon the ground truth data of LULC. You can modify the bottom stress and surface stress. So this is how LULC is actually being incorporated in the data, and then see how it impacts on the flooding. That's very important. You can see that the first one is actually without LULC. If you don't use LULC, you get actually this kind of left side. 99 super cyclone gives like this. If you use LULC, then this is the one you get actually. Sorry, I have made a mistake. This is without LULC. This is with LULC. With the LULC, the coastal inundation is less computed. That is all understood because your sea surface roughness and bottom roughness is changing a lot. That is actually preventing the coastal inundation. Therefore, you get less coastal inundation by using the LULC data. Okay, this is, we made a table at a different locations, how much it is making the difference. You always get with LULC less maximum water levels, therefore you can expect less inundation. Okay, this is again, we have used actually precipitation into account. One is only storm tides here, and in this case, we have used the upstream end freshwater and also precipitation. So by using this one, you have more inundation. because of the precipitation and freshwater discharge. You could see clearly how much inundation extra is calculated in terms of percentage. We have given the details in the paper, but I don't want to discuss in which pockets which are leading to more actually inundation because of the precipitation. Wherever you get more precipitation, it is expected more inundation. So that way it is actually making the difference. And this is the 2013 Phylline cyclone. You can see that the discharge is more actually compared to the 1999 cyclone from the river systems. So Brahmani, Baitarani and Mahanadi is contributing, for example, Baitarani is contributing much more compared to 1999. Okay, that means you have more precipitation in the case of 2013 Phylline cyclone. That's what in that river basin. That's more important. Okay, so and we have validated the model also because we know that how much storm tide. We all know that one for Phylline cyclone it is a recent one. In fact, we have been using our models for giving our forecast on a daily basis also, different lead times. So the model is actually really forecasting the model tide, and also observed tides and simulated tides are very well matching, and also storm tides. So this is just for a model verification part. And now we have done lots of experiments with the Phylline cyclone. Because as I told you, the Phylline cyclone is crossing the coast about 100 kilometers south of this basin. Therefore, you can't see much inundation because of this Phylline cyclone in the river basin. That's what we want to see, how much it is making the difference if the cyclone is crossing south of it. That's very important. One is actually 99 exactly passing through this deltaic region, but the other one, now 2013 cyclone is just passing south of the earlier one. Okay, so you can see that at various locations, how much storm tides are produced. Actually, this is, I don't want to go into the details of this one. And this is what is more important in terms of, inundation. Okay, for 2013 Phylline cyclone, we have a satellite picture before the event, before the cyclone, and after the cyclone, Landsat 8 satellite picture. I'm just comparing. Of course, this cyclone, after the cyclone, no, we got 1 week after the event was occurring. So therefore, it may not give exact precipitation, but wherever the heavy flooding was taking place, still after 1 week also you could see that in our model, the circle, oval shaped circle, you can see that this is the area which is got inundated in our model, but that was also seen even after 1 week, actually, that even after 1 week, same area got inundated through satellite picture. So therefore, it is a way of actually validating our model, how best these models can be utilized, provided you have all the information about the cyclone, not only the intensity of the cyclone, but how much it is giving precipitation, how much, whether it is crossing in the river basin or not, how much topography is being incorporated more accurately. All these things matter. And we can always, compare with the satellite data if it is available just after the cyclone happened. Okay, this is again 1999 cyclone. We are comparing again storm tides again at a different locations. What is the inference of this work actually? Okay, what is this gives? This is the first of its kind to compute coastal inundation on the Indian coast by incorporating the precipitation on the computation of inundation. It also helps to understand and quantify the contribution of hydrological components during any cyclonic event. So far, this is the first attempt which we made actually this work, because earlier precipitation, as I told you, we are not considering, we are just assuming that the storm tide, all the inundation is only made by storm tides. It is not true actually, because precipitation also makes a lot of difference in the calculation of inundation. Therefore, we have to take into account not only that if it is a river system, then you have to incorporate the upstream end, how much discharge fresh water is coming into the domain, so that you can see actually in the calculation of inundation. So these factors are being incorporated. Now we have a model, a system which can take care of each and every hydrological component. And also we have seen the importance, how much it is contributing on the inundation. So these things we have actually made a very detailed study, but I made very simple, but just because of the time restriction, but it's really huge work actually. It also provides a platform to improve further by prescription of finer details of the river basin. Still, river basins are not very accurately represented to some extent. Whatever the data is there, we can put it back into the model configuration. Therefore, it will always improve. And also, we need to incorporate the rainfall. Okay, we are not actually taking the rainfall, spatial variance of rainfall. We not considered actually. That we have to consider in the next level of improvement. Okay, so we have taken the every average because we all know that the precipitation doesn't be uniform in that area. So it will be, non-homogeneous in spatially also. Therefore, we have to consider that one also. So, and also we have to keep on improving our ground truth data. That's more and more from the in situ or from the satellite images. So this is the scope for the future work. So, and this work actually we communicated to JJR. I think it is in the first revision is over. So mostly it will be accepted soon. So this is the glimpse of the work which I carried out in the recent one on the part of coastal inundation, because ultimately for the public, what is required is storm surge 3 meters or 4 meters doesn't help anything. But how much coastal inundation is occurring because of that cyclone event? That's more important, so that a proper evacuation of the local population affected region is more important, so that it will be helpful for the mitigation or anything, for the disaster management. All the stakeholders can consider this type of information. Thank you very much. I think with this, I would like to thank again Dr. Mitra for giving an opportunity for this wonderful occasion, WMO Day. Thank you very much indeed.
Before Indira, Indira, please add. After that, I would like to speak for 1 minute.
Okay, sir. Thank you, Rao sir, for your very informative talk and the latest development in the coastal inundation research, whatever you are doing at IIT Delhi. And also, it is very nice to see that the post-event analysis of 1999 super cyclone, Odisha super cyclone also. Thank you, sir. Thank you very much. Mitra sir.
Yeah, these talks were so exciting that I could not resist to add just few comments. So Professor Mahanti's talk was so nice and showing the importance of ocean. And you see, that's why WMO has selected it so timely that the importance of ocean is being shown. And you all know that ECMWF has moved to a coupled NWP from 1990-20. So they are the leaders. So they are having a now coupled medium range ensemble forecast system. And one more thing, it appealed to me that what was happening in 1980s and 90s in NWP. You were worried about data assimilation, how much initialization model, and that is happening now to ocean and ocean data assimilation and coupled model. So this is the time for the ocean modelers and coupled modelers, ocean assimilation and coupled assimilation to start. So we are really very fortunate to have been in this field. And if you think over last 40 years, so much nice progress has happened gradually from atmospheric model to ocean model, then initialized ocean model, and now the coupled models. So ECMWF has shown the way, and I am sure all other centers will be following, including our Indian center. And I remember Professor Rao's work when I was in IIT some 40 years back. I joined CAS in 1983, almost 40 years. So at that time, the presentations of Professor Dubey, Professor Rao, we are happy that storm surge is being predicted and it's matching with observation. But tremendous improvement has happened. You see, the tropical cyclone prediction has improved, storm surge has improved. So now we are attempting about coastal inundation. So how much development has happened. So we are all very fortunate to be, I will say we are blessed to be in this field of research and operations and serving the society. And I feel time passes so fast that if you are engaged in work. So thank you very much. Very exciting two talks, and it shows the tremendous progress done in India. Thank you.
Thank you, Dr. Mitra.
Now I invite Dr. Ashish Rautre of NCMRWF to deliver the vote of thanks. He is also the secretary of IMS Noida chapter. So please, Ashish.
Yeah, thank you. Good afternoon to all. It is my pleasure to give vote of thanks in this auspicious WMO Day 2021 celebration. I, on behalf of NCMRW and IMS Noida chapter, extend a very hearty vote of thanks to the today's chief guest, Professor UC Mohanty, who spared time from his busy schedule to grace the occasion. Thank you, sir, for sharing with us your valuable work, suggestions, and basic of metrology, and it is interconnected with basic sciences, and your vast experience in this field. I want to extend my sincere thanks to Professor Edira. He agreed to give WMO guest lecture and share his valuable knowledge and research activities in ocean sciences. Thank you very much, sir. I express my heartfelt thanks to Head NCMRW and Chairman IMS Noida Chapter, Dr. Ekemitra, for his valuable support and guidance to make the event successful. I would also like to thank Dr. Raghavendra Asif and Dr. Akhilesh Kumar Misra from NCMRW to help support and technical arrangement to smoothly carry out the WM Day celebration. Lastly, I thank my friends, colleagues, research scholar, IMS member, and my executive member of IMS Noida chapter for their cooperation in making this function success. Thank you. Wish you a happy WMO Day 2021.
Can we take a snapshot? All cameras.
All cameras
please.
on. Yeah, that's a good idea.
Sir, who is class will take her?
Anybody, everybody take. We'll see whose is coming best.
Done.
Thank you, sir. Thank you very much.
Thank you. Thank you. Mohanty Saab, thank you. Bye. We'll see you again sometime.
Bye-bye.
Bye.
All the best. Yeah.
Thank you, sir.